Hello everyone. So today I'm going to present our paper Blockchain based root of trust management in security credential management system for vehicular communications. The authors are me, Arijit Sarkar, Sang-Yun Woon, Dr. Wenjun Fan and Dr. Sang-Un Chang. This is presented by me, Arijit Sarkar. So here at first I will describe the background related to the Vehicular Networking and Security Credential Management System SCMS. Our work is based on the SCMS. Then I will present the contribution scope of our paper. Then we will go through our proposed model blockchain based root management BBRM. Then I will present the analysis of our work. So, vehicular networking serves as one of the most important technologies required to implement lots of applications related to vehicles, vehicle traffic, drivers, passengers, and pedestrians. In vehicular networking, each vehicle has onboard equipment called OBE. This has a communication channel with roadside equipment called RSE. And RSE has communication channel with any application related server via the router and internet. So this is like a very high level diagram of vehicular networking. So in vehicular networking, OBE and RSE, they continuously exchange messages among themselves to drive safely and avoid any accident. But how to trust the messages received by any OBE or RSE from another OBE or RSE? An attacker may insert false messages. To prevent this problem, the sending OBE or RSE digitally sign each message and the receiving OBE or RSE verify the signature on the message before acting on it. And here to trust these signed messages, Security Credential Management System SCMS has been developed. SCMS has been developed by the Crash Avoidance Matrix Partners LLC, CAMP LLC, under a cooperative agreement with the US Department of Transportation US. Members of the CAMP LLC VSC5 consortium are Honda, Hyundai Kia Motors, Nissan, Ford, General Motors, Mazda, and Volkswagen. And this SCMS work is sponsored by the National Highway Traffic Safety Administration NHTSA. So SCMS is a public key infrastructure for vehicle-to-vehicle and vehicle-to-infrastructure security, can be commonly called as vehicle-to-everything V2X security. So SCMS issues are digital certificates for vehicles and infrastructure devices for trustworthy communications among them, and it is designed to maintain privacy both against SCMS insiders and outsiders, such as an adversary accessing the V2X channels at the time of the certificate use or any honest but curious authority. So this threat model motivates a decentralized PKI for the separation of the SCMS authorities, so that no single authority compromise breaches the vehicular privacy. So this is SCMS PKI early design in 2013. This is called a standard PKI hierarchy. So here the lines define the communication channel where one authority provides certificate for another authority. For example, root certificate authority provides certificate to policy generator PG, intermediate certificate authority ICA, and misbehavior authority MA. These authorities have different functionalities to facilitate, manage, and provide the digital certificates to end entities such as RSE and OBE. Then in 2018, the design of SCMS PKI is updated and the concept of elector-based root management EBRM came. Here the green dashed rectangle represents the EBRM. EBRM provides the root of trust for the SCMS PKI. In EBRM, there is a set of electors who manage and provide the Certificate of Root Certificate Authority RCA, and the certificates are managed in a distributed way. So our work is focused on this EBRM. In EBRM, the electors vote to select or revoke any root certificate authority. They do it by signing the RCA certificate, which is called root endorsement. Electors themselves are also selected or revoked using similar type of distributed voting mechanism. So why actually it is needed? Because RCA or elector certificate's validity period may end or a revocation may necessary. For example, if any RCA or elector misbehaves. In that case, the certificate of the RCA or elector need to be revoked and a new RCA or elector need to be selected. So electors, they have the power to change the RCA or elector using distributed voting mechanism, and elector based root management introduces ballot with number of votes. So in EBRM, elector cast votes by signing the certificate of a given RCA or elector votes. So these votes can be either for adding RCA certificate or revoking RCA certificate, or adding elector certificate or revoking elector certificate. So the votes for a particular certificate selection or revocation are aggregated into a ballot. So when a quorum of valid elector votes is presented in a ballot, then the ballot can be trusted and the respective certificate of RCA or elector can be valid or invalid. The value of quorum is defined in the global policy file GPF in SCMS, and these electors are not part of the standard PKI hierarchy in SCMS. That's why a different crypto system can be used in elector-based root management, EBRM. So we use blockchain in EBRM. So the problem here is that the electors in EBRM select the RCA, and RCA provides certificates to authorities like Policy Generator PG, Intermediate Certificate Authority ICA, and Misbehavior Authority MA. Though the electors are selecting RCA in a distributed manner, but RCA can be subjected to single point of compromise. Securing RCA is critical because it provides the root of trust for SCMS, which in turn provides the certificates and the trust in keys to the vehicles for the vehicular networking. So that's why we defend against the RCA compromise by having a blockchain to replace the RCA and manage elector certificate in a distributed manner. Another problem is that with a particular role of SCMS manager, so an agent of the SCMS manager collects the votes from electors in EBRM vote for selecting or revoking an elector certificate and RCA certificate. So after collecting the votes for a particular certificate, an agent of the SCMS manager provides those collecting votes to the Policy Generator PG. So here the problem can happen that the single point of compromise for this specific role conducted by an agent of the SCMS manager. That's why we introduce blockchain here to replace this specific centralized role of the SCMS manager. So in our proposed proposal, blockchain-based root management BBRM, we are replacing the voting process in EBRM using permission blockchain. In this case, we are using two types of certificate. One is root certificate or RC, where the electors provide the certificate to PG, ICA, and MA. and this replaces RCA, and another is elected certificate or EC, where the electors provide the certificate to any other elector. So RC is needed to select or revoke certificate of the authorities PG, ICA and MA, and EC is needed to select or revoke any elector certificate. And in BBRM, we established who can access, read and or write in the blockchain to support SCMS and vehicular networking. In BBRM, electors PG, ICA and MA has access to the blockchain, and where electors can read and write in the blockchain, and PG, ICA and MA have only read access to the blockchain. So what are the advantages of BBRM or applying blockchain in EBRM? So BBRM applies blockchain for two functionalities. One is RC to replace the RCA to make the SCMS simpler and get rid of the corresponding vulnerabilities, such as the RCA being the single point of compromise, and another is EC to manage the elector network control within EBRM. Another property is the immutability, which makes the transactions of the RC or EC generation and revocation more trustworthy, because the transactions cannot be revoked for manipulations once that transactions are included in the blockchain, and those transactions has been voted by the electors via the distributed consensus protocol. And another property is the transparency, which provides greater accountability, because the members of BBRM, EB electors, ICA, PG and MA can see who has voted for whom directly from the blockchain, where the votes are casted. And since BBRM uses blockchain, so the nodes connected to the network can have automatic synchronization with RC and EC states, and it also provides distributed consensus, which makes it appropriate for the voting protocol in EBRM. So here we will describe about the functions used in BBRM. The first four functions are called voting functions, since these functions are related to the voting process of adding or revoking EC or RC certificate. Add RC belongs to the voting for the selection of a RC, while revoke RC corresponds to the voting for the revocation of a RC. Add EC belongs to the voting for the selection of an EC, and revoke EC corresponds to the voting for the revocation of an EC. Transactions submitted using the voting functions contain the same payload format, meaning the same certificate format. However, the classification is made into four types to distinguish between the different objectives of the function. For example, to specify whether it is for adding or revoking a certificate and whether it is for EC or RC. We also have query function, which is used to read transactions from the ledger, which transactions are submitted using the voting function for an EC or RC. So in BBRM, an elector starts a voting round by broadcasting a transaction to support or revoke an RC or EC. Other electors, depending on the choice, can submit transaction to vouch for that transaction. If the initial transaction gets majority vote including the transaction itself, then the certificate in the transaction is selected. In BBRM, there is only positive vote, means when an elector supports a certificate, then only it provides vote for the certificate. Adding negative votes has additional complexities, such as increasing the blockchain size, more complex counting process, whereas adding positive votes makes it simpler. So now I will talk about the BBRM implementation. So we have used Hyperledger Fabric to build BBRM prototype, and the smart contract is implemented in Go language. So in ACMS it is said that 3 electors are needed for proof of concept and 9 operational electors are assumed for the actual deployment. That's why we implemented the BBRM prototype varying the number of electors, like for 3, 5, 7 and 9 electors. The experiment is conducted on one physical machine with Windows 10 operating system, which runs several virtual machines. Thus, the configuration of each virtual machine is shown in this table. So now I will describe about the analysis part of BBRM. So this graph shows the blockchain size rate, where the x-axis is the number of electors and y-axis is the blockchain size per event, which is so this is measured in kilobyte per event. So the event is one voting round for a certificate, which makes the certificate viable. Min votes and max votes define the minimum and maximum number of votes in an event needed for a certificate to be valid or invalid. So we did the analysis for 3, 5, 7 and 9 electors. For min votes, the size of one event ranges from 14.01 kilobyte to 34.93 kilobyte. And for max votes, the size of one event ranges from 21.01 kilobyte to 62.88 kilobyte. So this is the range to show how blockchain size can grow per event. So here I will describe the transaction scalability, comparing the maximum scalability in Hyperledger Fabric and BBRM. Although the performance of Hyperledger Fabric blockchain depends on many variables such as block size, transaction size, network size, hardware configuration, etc., the Hyperledger Fabric growth rate can scale up to 20,000 transactions per second with 2.9 kilobyte per transaction size, which corresponds to 1.829 to the power 13 terabyte per year. For our work, the scalability requirement for ACMS EBRM is significantly less. For example, RC changes once every 3 years. For our case, each RC generation revocation event and the corresponding EC events ranges from 18.68 kilobyte per year to 209.6 kilobyte per year, which is significantly less than the capacity supported by Hyperledger Fabric. This range is calculated considering the minimum votes in 3 electors to maximum votes of 9 electors. So another analysis I want to show is transaction throughput. So transaction throughput can measure how fast the BBRM is. It is the rate at which valid transactions are committed by the BBRM network for a defined period. So the verifiers such as ICA, PG, AMA, etc. need to be updated about the blockchain state in BBRM as soon as possible. Otherwise, if any RC or EC is revoked, but it will still be used by ICA, PG and AMA until result is not reflected on the blockchain. That's why this calculation is important. In the graph, we have number of electors in x-axis and throughput in y-axis, considering transaction per second and kilobyte per second. So if we consider the 9 elector case, which has the slowest transaction throughput rate and maximum blockchain size for one event among the 3, 5, 7 and 9 electors, the transaction throughput is approximately 3 transactions per second or 16 kilobyte per second. In this case, for one event, the blockchain size for max votes and min votes are 62.88 kilobyte and 34.93 kilobyte respectively. Thus, it is needed only few seconds to complete one event. So, we have also conducted other analysis such as latency research consumption, which is presented in the paper. So SMS uses EBRM, which provides the initial root of trust for the SMS PKI. Due to its importance to the rest of the SMS operations and eventually to the vehicular communications, we advanced the EBRM design and proposed and built BBRM, which provides greater decentralization, resiliency, and transparency. So, BBRM future directions include generalizing the BBRM design for a generalized framework and constructing BBRM adaptations to apply it to the other advanced PKI design. So, thanks for hearing the presentation. Any questions?